Okay, in the late 1800s, there was a French chemist by the name of Henry Le Chatelier, and he came up with something called Le Chatelier's principle. And Le Chatelier's principle explains how a chemical reaction will respond to being stressed out at equilibrium. So if you have a chemical reaction at equilibrium and you stress it out, maybe you stress it out by adding reactant, adding product, or taking away a reactant or taking away a product, then what happens is that reaction will shift to partially alleviate the stress and then get back to equilibrium. So the key word here is going to be partially. Okay, so it'll never fully restore like the concentrations to what they were, and I'll show you what that looks like. But we're going to go over adding and taking away reactant and product today, and then predicting which direction we will shift. So let me start out by giving you a generic equation. A plus B is in equilibrium with C. Okay. So let's say we go ahead and we stress out the system by adding some A to the system. So this would be an example of a stress. Okay. Anytime you add something, look at where it is in the reaction, and then you shift to the other side. Okay. So if A is on the reactant side, then I would have to shift to the product side. Does that make sense? So we're going to shift to the right. Now, shifting right means I will consume some reactant and I will produce product. Okay? So when a quantity of reactant or product is added, so I'm going to underline added here. Le Chatelier's principle says the system or the chemical reaction will shift to remove some of the added chemical. So I'm going to underline the word some. So basically, when I shift to the right to remove some of the A, that means I'm going to produce more C. So C will go up. I'm going to consume B, so B will go down. But since I'm not able to consume all of the A that I added, A had gone up overall. Does that make sense? Okay. Now, let's say I do something else. Like, let's say I go ahead and I add some C. Since C is a product, and you want to shift away from it, which direction will I shift? Yeah, so here we will shift to the left. And when I shift to the left, you will bring up A and B, and then you will consume some of the added C, but you won't consume all of it. So overall, C went up. Okay? Okay, let's talk about what happens when I remove something. So let's say I remove some B. So anytime you remove something, you're going to move in its direction because you want to bring it back to where it was. Now, you'll never bring it back to where it was originally, but you'll get close. So if I remove some B, since B is on the reactant side, which direction would I shift? Yeah, you would shift to the left. Okay, and when you shift to the left, C will go down, A will go up, B will never come back to where it was originally because I can only replace some of it, so that means overall B went down. Okay, and then another example would be if I remove some C, which direction would I shift? You would shift to the right because you want to bring some of the C back. Will I bring all of it back? No. So that means C overall is down and A and B are down because I'm shifting right. I'm consuming this to get over here. Okay. All right. So down here, when a quantity of reactant or product is removed, the system will shift to replace some of the removed chemical. Okay. So, and I'm going to give you a couple of other notes here to add. So anytime you're adding something, you want to shift away from it. So that means you're going to the other side. And then anytime you're removing something, you're going to shift towards it because you want to bring it back. Okay, so here they explain shift right and shift left. So if you are changing some reactants into products, then we are shifting right, okay? And then if you are changing some products into reactants, then we are shifting left, okay? All the notes that I had just given you on A and B producing C and what happens, I hope you had that stuff written down, because some of you asked me, like, you don't understand why your grade is where it is, and I watched that you don't even bother taking all the notes. So if you're not actively engaging in learning, it's not going to happen for you. Okay, so let's come over here. Let's take a look at the sample problems. So here we've got some HI being added. Where is HI in the reaction? Is HI a reactant or a product? Product. So I'm going to highlight it over here. I'm going to make myself a note that we added some HI. That was the stress that you caused to throw the equilibrium off. Which direction will I shift when I add HI? Yeah, you shift left because you want to move away from it. Anytime you add something, move away from it. So that means we're moving towards the reactants. When I move towards the reactants, what's going to happen to H2 and I2? Will they go up or down? Yeah, they'll go up, because anytime you are shifting left, you're trying to bring the reactants back up because you're consuming product. So that means I'm going to consume some of the added HI. Keyword is some. I'll never consume all of the added HI. So that means overall HI did what? Did it go up or down? Up, because I was never able to consume all of it by shifting left. Okay, so once you get back to equilibrium, this is how the amounts would look. Okay, all right, now let's take a look at another example. At the bottom of the page, here we've got a solid, and it's in equilibrium with its ions. So anytime you're dissolving something and then recrystallizing it, it's called solubility equilibrium. Okay, so dissolving and crystallizing are happening at the same rate here. And here it says that some hydroxide ion is removed. Is hydroxide a reactant or a product? It's a product. So I'm going to highlight the hydroxide ion, and I'm going to make a note that some of this is removed. Okay, they removed it by adding an acid, because acids consume bases, and hydroxide is a base. So when I remove some of it, in which direction would I shift? Yeah, because anytime you remove something, you want to go in its direction, so we have to shift to the right. So we're moving towards the products, okay? Now, when you shift to the right, what happens to the amount of Ca plus 2 here?
Goes down.
I'm shifting this way, which means I'm consuming reactant and producing product. It goes up. And then if I had removed OH, but I'm never able to replace all of it. Overall, it was down. Okay. Let's turn to the next page. Okay, you take a look at question number 1, A and B, and let's see what you guys come up with. Okay. All right, now, this one says they added iron 3 nitrate, it dissolves, and then these are the 2 ions that are produced in the solution, okay? We only care about the one that's actually in the reaction that we're looking at. Which one is in the reaction? Okay, so I'm going to highlight the Fe plus 3. Okay, other one is irrelevant. So here what's happening is we are adding some more of the Fe plus 3. Anytime you add something, you want to shift away from it. You want to make sure you memorize that. Okay, so if I add more Fe plus 3 and Fe plus 3 is a reactant, which direction will I shift? Okay, so we're going to shift to the right. Now we want to explain what happens when we shift to the right. When I shift to the right, will I consume all of the Fe plus 3 that I added or some? Okay, so here we will consume some of the added Fe plus 3. Okay, that's really all I'm looking for here. Now, if we take it one step further and we talk about what happened to the quantities of things once we got back to equilibrium, if I shift to the right, is this product going up or down? Yeah, so this would have gone up. And then would the SCN negative on the reactant side go up or down? Down, because you're consuming reactant to get to the right. Okay, so did I consume all the Fe plus 3? No, just some of it. So that means overall it went up. Confusing? We're okay. Okay, let's look at the bottom at the last paragraph and then we'll do some review questions, okay? So if you're initially starting a reaction and you're using a solid and you decide that you want to get to equilibrium as soon as possible, a couple things you can do. Add a catalyst and then use a powdered solid. Okay, so when a catalyst is added, initially, you will get to equilibrium sooner. Okay, that's a benefit. Also, if the initial reactants have a greater surface area, so if you use a powder initially, you will also get to equilibrium sooner. But if you're already at equilibrium and you're trying to maybe see if it affects things by adding a catalyst or adding a powdered solid, you're not going to observe anything. So if you add a catalyst, it's going to actually increase the forward and the reverse rates the same amount. So there's no effect on equilibrium, okay, if you're already there. And then if you're at equilibrium and you're like, oh, I'm going to add some more powdered solid, again, nothing's going to happen. Okay? All right, now let's take a look at the review questions on the next page. So let's turn the page, and I want you to do number 1, A and B, or review questions 10.2. Okay? So let's go over here and do 1, A and B, and then let's go over it. Okay, so for number 1, we have a reaction, and we're going to add some NO. NO is a reactant. Okay, so that means we're going to shift in which direction? Yeah, you want to shift away from it, so shift to the right. When you shift to the right, what happens? We'll consume what? All or some of the added NO. Okay, we good? Okay, homework is open.